Let's start things off by finding out more about SSL certificates. What are they exactly, and how do they work? Let's begin with the simplest explanation and then get more technical from there. The way that the public most commonly knows an SSL certificate is that it's the thing that triggers the little padlock or perhaps the green bar at the top of their web browser. What that indicates is that the web page is using HTTPS for secure communication. The most basic way to communicate on the web is using HTTP. HTTPS is the secure version of that. That's what the S stands for, is for secure. You may have even noticed that sometimes when you see a URL, sometimes it's HTTP and sometimes it's HTTPS. When we talk about secure communication, what we're talking about is data privacy and data integrity. The fact that someone can't snoop on our data and see what's being sent, and they also can't modify it while it's in transit. Now, a certificate implies that it certifies something. So what does it certify? It certifies the ownership of a public key. We'll talk more about public keys and the role that they play in cryptography a little later on. For now, just know that that's what it's certifying. It certifies who owns a particular public key, and that's used for encrypting data that's sent between a browser and the remote server. That's how we're able to guarantee data privacy and data integrity, is by using encryption. The SSL in the name comes from Secure Sockets Layer. That's just a protocol that's used for communication. In the earliest days of the web, if you wanted to use HTTPS, then it was using this protocol along with your certificate and your public key in order to communicate. Now in 1999, around the time that the web was about 5 years old, a new protocol for communication was introduced, which was TLS, or Transport Layer Security. And it's considered to be a superior version that's become far more common than SSL. And the certificates really don't depend on which protocol we use. The certificate is just certifying the public key, and these two communication protocols are using that public key while they communicate. So it really doesn't affect it. But the thing is that the name SSL has stuck. Even though TLS has now been around for 5 times as long as SSL, no one really uses SSL for communication anymore. They really use TLS, but we still call them SSL certificates. For this reason, you actually will see them called by many names. Most commonly, they're SSL certificates, but some people call them SSL/TLS certificates. Some people just call them TLS certificates. Some people try to avoid including the protocol altogether and just refer to them as digital certificates. Or because they're certifying a public key, you may see them called public key certificates. Or because they certify the identity of the person who owns the public key, you may see them called identity certificates. All of these are valid names, they're all interchangeable. Still, SSL is the most common name that you'll see out there. But you should recognize all of them and understand why those different names exist. So what's inside one of these certificates? Well, it certifies the ownership of a public key, so we need to know something about the person that owns it. So we have the organization, we have the URL, the state and the country. We also have the valid date range for the certificate. Certificates aren't valid forever. They're certified just for a certain amount of time, and they're certified by an issuer, someone who actually says, yes, I am going to validate the fact that this organization, this URL, owns this public key. So all of this basic information, as well as some technical details like what type of encryption it uses, is all going to be put into a file, a certificate file. And that's typically a file that ends in .crt or sometimes .cer. Now the contents of that file is not going to be readable easily by you. If you open up one of those files, you're going to see something that looks like this. What that actually is an encoded version of that information. And it can be decoded. You can take it to a website, you can run some tools on your computer that will decode it, but this is a way to compress it down and make it good machine readable code that can be passed easily over the internet. Now that we understand a little bit more about what SSL certificates are, let's make sure you understand their purpose. Their primary purpose is to be used with encryption. It's so that we're able to encrypt communications and communicate securely between two different computers, usually a browser and a remote server. They also tell us something about the identity of the person who owns a particular public key. So they have that purpose as well. And beyond that, they also tell us something about the trustworthiness of that person. Now, there's all sorts of problems related to both identity and trustworthiness, and we're going to touch on those a little later on. But these are the main purposes. The number one purpose by far is to be able to use this key for encrypting data. In the next movie, let's talk a bit more about how that encrypted secure communication works. In the previous movie, we learned that what SSL certificates certify is the ownership of a public key. In this movie, I want to talk a bit more about public keys and the role that they play in secure communication. To do that, we're going to need to talk about handshakes and cryptography. But don't worry, I'm going to keep it fairly non-technical so that everyone can follow along. The first thing we need to learn about is something called symmetric key cryptography. The idea is simply that we encrypt data using a password. So we take some data, we take a password, we put it into an algorithm, and what we get back is some encrypted data that can't be read. We can then later come back and decrypt that data by taking the same password, putting it into an algorithm with our encrypted data, and what we get back is something that is decrypted or readable. So the name symmetric key is a fancy way of saying that it uses the same key for both for encryption and for decryption. And our key is the password, and it works very much like a key would on a normal lock. In fact, we can think of symmetric key cryptography as being a box that we can lock. We can open it up, we can put data inside of it, and then we can close it and lock it with a key. Then it's encrypted and it stays locked, and the only way to unlock it is by using that same key to open the door and get the data back out. That's symmetric key cryptography. Now, public key cryptography works a little differently. It's also named asymmetric key cryptography, which gives you a tip about what's different. We don't have symmetric keys, we have asymmetric keys. That is, they're not the same anymore. Instead, we have a pair of mathematically linked numbers. These are numbers that are derived from multiplying prime numbers together. You don't need to worry about the mechanics of how that happens. Just know that at the end, you end up with two numbers that are linked together, and we refer to them as the public key and the private key. As the name suggests, the private key should always be kept secret and secure. It belongs to you and you alone. But the public key can be shared widely. We don't care who has it. We can send it in our emails, we can post it on the internet, we can share it with the world. The advantage of having two linked keys that are not the same is that then data can be encrypted by the public using our public key that's widely available, and it can only be decrypted using our private key, which only we have. So it allows the public generally to be able to send us private messages that other people can't read. Let's take that locked box example again. Let's imagine now that we have a box with two locks on it. On one side, we have a lock for the public key, and on the other side is a lock for the private key. Now the public side is unlocked. We can open it, the public can put a piece of data inside, and then they can lock it using our public key. Once it's locked, even another public key can't be used to open it again. Now it stays locked, and we can submit it even over the internet. It's encrypted data that's completely safe. At that point, the person receiving the data can use the private key that they have to unlock the private side of the box and retrieve the data and read it. That's how public key cryptography works. So now that we understand the difference, we're ready to talk about handshakes. This is also referred to as SSL or TLS handshakes. Both of those communication protocols use it. The basic idea is that we're going to use public key cryptography in order to communicate. So let's walk through the steps. First, a browser is going to send a request to a secure server. The server is going to say, hey, I see you have a secure request. Let me send you back my SSL certificate, and I'm going to send you back my public key and other data about my identity. The browser is going to take a look at that, and it's going to decide whether that public key is something that it can trust. And it's going to do that by confirming that this certificate is valid. There are a number of different ways that it can do that. The simplest is it can just look and see if the expiration date has passed yet, whether the certificate is still in its valid date range. It can also look at who issued the certificate to see if that's someone that we trust. If the browser decides that this is something that we can trust, then it can use that public key to encrypt a very long password and send it to the server. It's the same as having that box, opening it up, putting data inside, and locking it with the public key. The data that goes inside is going to be this password. Then that can be transmitted securely over the internet. The server can then decrypt that data using its private key in order to retrieve that very long password. Now here's the important point. The server and the browser now both possess this same password. That's the beauty of public key cryptography. With symmetric key cryptography, it works great as long as both people have the same password, but it can be really tough and challenging to share that password publicly without someone eavesdropping on it and finding out what it is. With public key cryptography, we can do all of this in public and not have to worry. Now, both the server and the browser can switch over and use symmetric key cryptography, using that shared password to encrypt all future communications. So why do it that way? Why switch over to symmetric key cryptography when we were doing so well with the public key cryptography? Well, it's because it allows us to have the benefits of both technologies. Public key cryptography is great for being able to communicate private communication fully in public. But the problem is that the algorithms that do that are quite slow. Symmetric key cryptography, on the other hand, can be difficult to send that key publicly, which makes it hard to be able to share data anonymously over the internet. But once we have a shared key and we have a password that we can both work with, then it's very fast. So we use public key in order to swap a password, and then we switch over to symmetric key in order to get this speed advantage. So again, just to recap, the SSL certificate certifies the ownership of the public key. The public key is used to exchange a password in public or over the internet, and then that password is used to encrypt all data between the browser and the server from then on. One additional advantage is the fact that all of the passwords that are used for this encryption between the browser and the server are going to be temporary and not reused. It's a one-time password just used for this one conversation that's happening between the browser and the server. Other browsers are using a different password. And in the future, if we try and contact the server again, we'll get a new password because we'll go through that same handshake process again. So the passwords are temporary, and that allows us to help keep that exchange data secret as well. In this movie, we're going to discuss why it has become urgent that web developers start using HTTPS on every single website. As our use of the internet has evolved, so has our usage of HTTPS. When the web was first created, HTTPS was there at the beginning, but it was used primarily for encrypting e-commerce pages. We knew if we wanted to buy something online, we needed to have a secure way to do that. So we could send our credit card information securely over the internet using HTTPS. As the web continued to grow and develop, more information started going online, and people started putting whole areas of data online that needed a password to be able to get into them. Those password-protected pages started using HTTPS, because if we need a password to protect them, then we should also keep them secure by encrypting them whenever that information is transmitted over the internet. Otherwise, it's freely available to anyone who might be snooping. So as that effort progressed and we saw more and more of those pages start to use HTTPS, at some point around 2010, people realized, those login pages that you're using to get to those password-protected areas, if they're not already on HTTPS when that page first loads, then you're sending an insecure request in order to get access to a secure area. That means that that password that we're sending from that form is being sent in the clear over the internet. So we saw a big effort to get everyone to start to use HTTPS on their login pages. And those login usernames and passwords would be encrypted when they're transmitted. And then around 2015, we saw another change where HTTPS started to become the default for all pages. We began to realize that data privacy and data integrity matter for everyone all the time. And we could prevent a lot of malicious activity on the internet if we could just get everyone to use HTTPS. And that change has happened very quickly. In January of 2014, 26% of page loads were using HTTPS. In January of 2018, that number had jumped up to 68%. That's a huge change in a very small amount of time. Of the top 100 websites, 81 of them use HTTPS by default now. That's major websites like Google, YouTube, Facebook, LinkedIn, Wikipedia, Reddit, Yahoo, Amazon, Twitter, Instagram, Netflix, eBay. All of these sites are all using HTTPS all the time. And that's part of what has accounted for that huge jump in page loads using HTTPS. But that's the major companies. What about everyone else? Well, at the same time, there's been a very important effort called Let's Encrypt. It's a project of the Internet Security Research Group. That's a consortium that has backing from a lot of these big tech companies. And it launched in April 2016. And the project goal was for all web servers to use HTTPS. Now, those big companies were already doing it, but what about everyone else? They decided to make the process as simple as possible. So they started offering free certificates, so it wouldn't cost anything, and they tried to take steps to simplify the setup and maintenance of these certificates. So there was as little friction involved in getting this process going as possible. They recently announced that they have over 50 million active certificates out there, and that number is growing rapidly. So it's never been easier to implement HTTPS than it is now. At the same time, there's been important changes happening in web browsers, led primarily by Google Chrome. In January of 2017, Google Chrome made a change and they started marking all HTTP pages, that's the non-secure pages, which have a password or a credit card field on them as being not secure, just to provide a big warning. Hey user, this page that you're about to put your password or your credit card in, it's not a secure page. In October 2017, they took another step forward and they started marking any page with any form on it as being not secure. And also, if you thought you were in incognito mode and you might be privately browsing, they also marked those pages as not being secure. Then in July 2018, they're taking another step forward and they're marking all HTTP pages as being not secure. Their overall goal is to help users understand that HTTP sites are not secure. Let's take a look at what that's going to look like. So normally an HTTP page would look like this, example.com, and it wouldn't say anything next to it. The change is that all of those pages now are going to say not secure. And what you're going to see over time is that not secure warning is going to become more and more prominent. They're really going to start to let people know, hey, this page is something you need to worry about. It's a buggy page because it's not secure. Now, Google Chrome is leading the charge on this, but other browser makers are following right along. They're also going to make another change to HTTPS pages. Those pages right now get a big nice warning that says, hey, this is a secure page. You should feel good about it. That's going to start going away. You can see that starting September 2018, they're going to go from having a green lock with the secure word next to it. They're going to change it from being green and take away the word secure. And then eventually, they're going to take away the lock altogether. The idea is that you should just expect that the web is secure and you'll get a big nasty warning if it's not. So that's what's going to happen. It's going to happen to your users. So it's very important that you implement HTTPS as soon as possible. It's a best practice that improves web security. The web is quickly moving to all HTTPS. Setting it up has never been easier. And at the same time, it's important for us to do it because if we don't, your users are going to start being alarmed by the